Good morning, everyone. Today we will study about abstract syntax trees, how to construct them, how to traverse abstract syntax trees, so on and so forth. So far what we studied is we have seen how to design a parser or a syntax analyzer. So if you see a parser, so you have this is your parser. It takes programs or strings as input and checks whether a given input program is a valid string described by the context-free grammar associated with that language. So it outputs yes or success if this input string W belongs to the language described by the context-free grammar. And it outputs no or it rejects if the input string W does not belong to the language described by the context-free grammar. So this is success or accept. This is failure. So, but this is not enough for the rest of the compiler. If the string is not a valid string described by the context-free grammar, then this is all right. Okay, this you just emit appropriate error messages saying these are the syntactic issues I found in your input program. You emit that you emit those error messages and then you exit. That is all right. But on the contrary, if the program is a valid string described by the context-free grammar, then you have to hand over that program to the rest of the compiler infrastructure. So there are two ways to handle this. So on successful parsing, so we are looking at on successful parsing, what should we do? So there are two approaches here. One approach is if you see during the parsing algorithm, the parse tree is kind of implicitly constructed. It's not explicitly constructed. What we can do is we can modify the parsing algorithm slightly so that we can have a concrete parse tree available to us. Concrete parse tree available. You can construct a concrete parse tree during the process of parsing. Earlier, this parse tree construction, it is implicit. Okay, there are no data structures which explicit data structures which hold that parse tree. But what we can do is we can make this parse tree explicit or concrete by modifying our parsing algorithm suitably so that the parse tree is also constructed during the as the parsing algorithm is carrying out its execution. And then once we have the concrete parse tree, from the concrete parse tree, we can construct what is called as an abstract syntax tree. You can make a parse over the concrete parse tree, and you can construct an abstract syntax tree. So the other approach is it is possible to directly construct the AST also. This is also possible. Directly construct AST during the parsing process. This is also possible. So just let's review what this AST and parse tree is. We have seen this before, But for the sake of completeness, we will see it one more time again. So if you have something like E goes to E plus E and ID, an extremely simple grammar, and if the input string is ID plus ID plus ID, then we know we can construct a parse tree like this for this input string. So this is the parse tree. And then the associated abstract syntax tree, ID is equal to E plus E. Oh, sorry, I made a mistake here. Let me redraw. I was a bit anxious. So we have E goes to E plus E. This is ID. This is ID. This is ID. And the associated AST is this. In the AST doesn't contain the exact derivation information. And in fact, the rest of the compiler doesn't need to know the exact derivation information. So this is the AST. So once the compiler has the AST, it can do semantic analysis on it. It can do certain high-level optimizations on it. It can do, it can do the intermediate generation. This is a tree structure intermediate representation, and it can transform this intermediate representation into a form which is much more closer to the target machine code or the target assembly language. So all these things, many things are possible once you have the AST. Or we can write an interpreter which make a pass over the AST and interprets the program. So once we have the AST, we can do many things like semantic analysis is one. Okay, some high-level optimizations. Like maybe there is an optimization called as function inlining. You can do inlining or loop interchange, things like that. Or you can lower AST to linear intermediate representation, which is closer to the target machine code. Or you can directly interpret the AST also. So there are many possibilities that are there once we have the AST available to us. So you can imagine how once we have, let's say, if a concrete parse tree is given to you, how we can construct an AST from the concrete parse tree, you can kind of easily imagine. So let's say it is possible for us to do a post-order traversal, do a post-order traversal on the parse tree. So when you do a post-order traversal on the parse tree, when you hit a leaf node, when you hit a leaf node you create an AST node like this. You start from here, you start traversing this parse tree in a post-order form, that is visit the left subtree. So like, for example, when you are here, you say visit left subtree, visit right subtree, and then process the node. So in that process, when the post-order traversal algorithm hits the node ID, it creates an AST node associated with this terminal symbol ID. And then what it does is the post-order traversal algorithm, it returns it this ID to the pointer to this ID to this. And then what when you are processing this node, you don't do anything, you just pass this pointer up to its parent. So at this node, when you are processing, you have processed the left side, left subtree, and then you go to the middle node, which corresponds to plus. When you hit the plus, what you do is you create a node plus. You create a node plus. And you pass this AST node to the parent. Similarly, you come down along this path, and when you are at ID, what you do is you create another AST node ID, and you pass this pointer up to its parent. And the parent again passes this pointer up to its parent. And so now all the children are processed. So what you do is the routine, the post-order traversal routine at node E, what it does is it attaches the left and right IDs, this one and this one, it creates to the plus node. And then it passes the pointer to the plus node up to this, the addition node up to the parent. The same thing happens. So this plus node, when the post order traversal algorithm visits plus, what it does is it creates this an AST node plus, and it passes this the pointer to this node up to the root. All right, and then again here when it visits this ID, it creates an AST node associated with ID. It passes this information up here to this node, and then it passes this information up here, and finally this plus and this ID are put together. They are attached to the what is coming from this path, and what is coming from this path. They are attached to the plus node, and finally this AST will be created. This is what that will be created. So you can easily imagine that given a parse tree, concrete parse tree to you, we can write a post-order traversal routine on the parse tree, and as a result, we get an AST out of that post-order traversal. Good. Any questions here? You're all doing all right? How many of you are with me so far? So what's the question, Ayush? I didn't get your question. So there is a question on, could you formally define what is an AST? Good, good. So we will see what is an AST. In fact, we will exactly look at the data structure and see what is, so what AST is. So, but simply speaking, AST is a tree representation for your program. It's a tree representation. For example, what you are seeing is AST is for expression trees. So this is an expression tree. This is an AST for an expression tree. But let's say, so how does an AST for an if statement look like? So if you see, so the AST for an if-else statement, if you see, it has 3 subtrees. One subtree corresponds to the expression, the Boolean expression in the if statement. And another sub-expression and another tree corresponds to the if part, and another subtree belongs to the else part. Similarly, if you think of a while statement, the AST for a while statement, so it will have two parts. So one part is a subtree, one child is an AST for expression, that is the Boolean expression, and another is the AST for the block statement that is present in the while statement. So for every construct that you have in your program, for every construct that you have in your program, you can imagine a data structure, an AST, associated with that construct. So in the how does the data structure for an AST looks like is what we will see in the rest of the class. We will see two approaches for the AST data structures. So AST data structure. We will see two approaches. One is by using structures and unions in C. We have to use structures, unions in C. How do we do? How can we capture the AST? Second is using object-oriented approach. If you use classes and inheritance. So here we use classes and inheritance. All right. And then we will see two traversal approaches. Okay, AST traversal approaches, we will see two traversal approaches. Specifically, so there is one approach which is a naive approach. There is another approach. We will see the issues associated with this naive approach. And then there is another approach using visitor design pattern. So this is the plan for the rest of the lecture. In order to make in order to get some intuition, we will start, we'll just handle expression trees. And at the end of the class, we will see how a similar idea can be lifted up and applied to different language constructs that you have in your programming language. Now let's take a code example. We'll take a code example and see what is happening. Let me stop sharing. Yeah. Are you able to see the Visual Studio Code editor? Good. Thank you, Rishabh. Yeah, so let's see ast.h. So if you think about it, so all the AST nodes, this is the structure. Focus your attention from line number 18 to line number 38. So this is where we are defining a structure which can represent any AST node in your AST tree. And so if you see your AST node, it can be a binary operator with addition, or it can be a binary operator with a multiplication operation associated with it, or it can be a ternary operator, or it can be a simple literal value, or it can be a while statement, or it can be a for statement, so on and so forth. So what we do is this, the field on line number 19, it will tell you what is the node type of that particular AST node. What is the node type of that particular AST node? The field node type will tell you. And if you go up, I have here on line 2, there are different AST node types that that we are defining. One is like, for example, one AST node type is it can be binary operator, it can be ternary operator, it can be an integer literal. Later on, let's say if you want to extend this so that let's try to close this. Yeah. So later on, if you want to add support to for statement here, you may want to have something like, it's a for statement. You can add a new AST node type for statement. And so if you want to support while statement, then you just have to say it's a, you can add one more AST node type, while statement. And associated with every AST node type, let's say if the node is a binary node, then associated with it, there is a structure. You can see here, there is a structure, and this structure has 3 fields in it. One field tells what is the operator associated with that binary node, whether it is an addition operator, multiplication operator, so on and so forth. And it has a left child and it has a right child. Left child corresponds to the left subtree of the binary operation, and the right field points to the right subtree. And if you go up and see, you will see, like, for example, in this particular AST definition, we are supporting 4 kinds of binary operators: add, subtract, multiplication, and division. And similarly, if the AST node, if it is a ternary, if it corresponds to a ternary operator, then the node type should be set accordingly, number 1. Number 2 is, you can see that there are 3 fields to it, okay, but is corresponding to 3 different operands for the ternary operator. And on the contrary, if the AST node, if it corresponds to a literal value, then, and in this particular case, we are assuming that the literal value can, is only integer literal value is possible, then you have only one field, int lit value. And then the node type should be set accordingly. So if you want to support one more, for statement, maybe we have to have something like AST for struct AST for statement, and then you have to add fields associated with like different fields associated with, like, you may want to say for statement, it will have 2 fields. One is an expression and other is statement, AST node statement. So like this, you can add support for new AST node types by extending this AST node structure. And one thing you can notice is each of these structures, they are kept in a union. So then that means the memory allocated to the AST node is the memory that is necessary for the field that is there on line 19, and the max of the memory is required by the different structures that are present within this union. So if the node type is binary node, then this structure becomes the AST EXPR binary op, or the binary node structure or the binary node field becomes active. And if the node type is ternary node, then the ternary node field becomes active, so on and so forth. This is how we will store, this is how we will define the structure for an AST node. And then this is present in a file called ast.h. And you can see, there are three functions: get AST node binary op. So when you want to create a binary node an AST node corresponding to a binary operator, then you can call this function by passing a pointer to the left AST subtree, and by passing a pointer to the right AST subtree, and mentioning what is the operator that is associated with that node. So if you go and see ast.c, and if you see this is the code from line 5 to line 19, you can see the code associated with creating a binary AST node. What do you do? On line 11, you create the necessary memory for that AST node. And on line 13, you set what is the binary operator. Line 14 and line 15, you set up the children. And line 16 is where you tell that, whether it's an addition operator, multiplication operator is what you will do on line 16. And on line 13, what you do is you specify that the AST node that you are creating, it is a binary operator node. So there is a question on what is the use of ANTLR. So see, I will answer this question. So let me answer this question. So it so turns out, usually in the when we construct a parser, using Flex and Bison, you have to explicitly construct this AST tree by yourself. But when we use ANTLR provides what are called as a parse tree traversal routines. So understand the ideas from today's discussion and then see how you can use these ideas while using the ANTLR tool to do semantic analysis. Whether it is necessary to construct an AST, like because the ANTLR provides tree traversal routines, you have to decide whether you want to use those tree traversal routines to explicitly construct an AST and work with it, or you can get around it and take a different approach to solve the problem in your project. So that's a good question, Apurva. So it's think about that question. So understand the ideas from today's lecture and see how these ideas can be applied when you are designing your semantic analyzer, when you are designing your code generator using the ANTLR parser tool. It's a very good question. Okay, similarly, there is line 21 to line 35. It contains the code for creating a AST node associated with a ternary operator. So on line 29, you are saying that the node type, that the AST node type, it's a ternary operator. And you can notice that we are not explicitly specifying what ternary operator it is, because I kind of assume that there is only one ternary operator that we are working with. That is, like the C thing. Like for example, if A greater than B, question mark, whatever, E1, E2. So this is 1, These are three operators. I assume this is the only possible ternary operator. But if your language has more than one ternary operators, then you may also want to specify what is a ternary operator type, in which case you may have something like node dot uh, ternary node dot op type ternary operator type. You may want to specify what is the exact ternary operator that is associated with this AST node. Let's keep going. So yeah, so once such a AST is constructed for you, once such an abstract syntax tree is constructed for you using this approach, like in this particular case, it's an expression tree. One thing that you can do with this expression tree is you can print the expression in a postfix form. So if you look at the postfix, then there is a function here, void, which print postfix function. So to this print postfix function, we can pass the root of the AST to this print postfix function. So what do we do here on line 51? We are checking if it is what is a node type. Is it a binary operator? If it's a binary operator, then you traverse the left subtree, you traverse the right subtree, and then you have a switch statement which checks whether the operator associated with that node is add, subtract, multiply, or division, and then it prints the corresponding operator there. Similarly, if it's a ternary operator, then what we are doing is we print the first subtree, process the second subtree, process the third subtree, and then we print the ternary operator there. And finally, if it's an integer literal, that if it is a leaf with no children, then you just print it as it is. So this is how you can write a tree traversal routine on your AST. You can also write a print post prefix traversal routine on your AST. Or you can write a evaluate tree routine by traversing the AST. Or you can do a type checking routine on the AST. Like for example, what do you do with in the case of type checking? You try to get the type of, if this is your AST plus A, B, you try to get the type of A, pass it here, pass the type of A to the parent, and the parent will check whether the type that is coming from the left side and the type that is coming from right side, they are compatible with each other or not. If they are not compatible with each other, they will you will generate a semantic error or type checking error. Like for example, here along this side you are getting a bool type, along this side you are getting a float. Then you can say there is a type mismatch. We cannot add a Boolean operand with a floating point value. So this is one approach for if you take the structures and union approach, this is how you will end up designing an abstract syntax tree for your in the compiler, and this is how the traversal routines on the abstract syntax tree looks like. Now let's try to take a different approach for AST traversal. That is using the object-oriented approach. Right. Yeah. So in the object-oriented approach, what we do is we have a base class called as the AST node. We have a base class called as AST node, and and then we will associated with every node type, we will have a derived class. So for example, here associated with binary operators, we will have a class called binary AST node. And this binary AST node, it is derived from AST node base class. And what are all the fields in the binary AST node? you can see on line 12 what is the binary operator. That is one field. And then there is one more field for the left subtree, and there is one more field for the right subtree. That is LHS and RHS. Actually, this is no, that field name is not, it's not left hand side or right hand side, it is left subtree and right subtree. And one important thing you need to make a note of here is the left and right subtrees, they are of type AST node of the base class. All right. Because the left node can be a binary AST node, or it can be a ternary AST node, or it can be an integer literal node. So you don't know what it is. In order to handle this, you use the AST node as the type, AST node star as the type for the left subtree variable. Similarly, the case with the right subtree variable. All right. Similarly, if you go to the ternary associated with, if a AST node associated with AST nodes which are which hold ternary operators, we will have a class, and this will have, we can see that there are three fields here, that is first subtree, second subtree, third subtree. And since we are assuming that there is only one kind of ternary operator in our programming language, we are not storing what is the ternary operator that is associated with this node. If there are more than two ternary operators, then you need to have one more field which tells what is the exact ternary operator associated with this node. And again, the important observation is the first subtree can be a binary subtree, the second subtree can be a ternary subtree, the third subtree can be associated with a integer literal. So in order to handle these different types for the subtrees, you tell the type of these variables as associated with the base class, that is AST node. And if you go and look intlit node, then intlit node, it has only one field, that is the actual integer literal. Great. So this is how we can design a class hierarchy for representing the abstract syntax trees using object-oriented approach. So now, once you represent your AST using this approach, you want to write tree traversal routines. One approach for doing the tree traversal is like, for example, you have a function called as you want to do a postfix traversal on the AST node. Then in the base class, you will define a virtual function, print postfix. I want you to think what will happen if you don't use the virtual keyword here on line 7. Think of it. Okay, that's a homework problem. So why virtual function? Why we need to define this traversal method as virtual? We have to use this keyword virtual. So that is a homework problem for you. So in the binary AST node, so you will have a method which implements that method that is there in the base class AST node, that is print postfix method. So what do? You traverse the left subtree, you traverse LHS print postfix, you traverse the left subtree, and then you traverse the right subtree, and then you print the binary operator associated with the current node. So one interesting thing you need to note here is, so when you make a call to LHS, I will revisit this idea a bit later. Let's go ahead and see. So now similarly, when you are working, when associated with the ternary AST node, when you have print postfix, then you first traverse the first subtree and the second subtree and the third subtree, and then you print the operator associated with the current node. And here finally, if you see for the int literal, all you have to do is you just print the int literal, and that's what the print postfix function does. So so why we need to use that virtual keyword is, so here when we are calling the print postfix function associated with the first subtree, the first subtree could be a binary subtree. If it is a binary subtree, then you need to call the print postfix function associated with the binary tree node. Similarly, if the second subtree, if it's a ternary node, then you want to call the print postfix function associated with the ternary node. And in order for us, and you only get to know whether first is associated with a binary tree node and second is associated with a ternary node only at runtime. By putting that keyword virtual in the base class, what happens is late binding of functions will happen. So, and at runtime, we will know exactly whether first is holding a binary tree node or a ternary tree node, and the appropriate print postfix function will be called. If you don't keep that virtual keyword, then this doesn't happen. So this is how you can write a postfix traversal routine on an AST structure represented using classes and inheritance. So now if you want to implement a print prefix traversal routine here in this program, what you need to do is, for example, in the base class, you need to have something like this. Control B, print prefix, and then here so like this, what you do is you go to every class and then you implement this print prefix method in every AST class. So this is one approach for representing ASTs and traversing ASTs. But the problem with this approach is you can see that every time you want to do some kind of tree traversal, you have to go and clobber your whole AST class hierarchy. Let's say if you want to implement an evaluate function, so what do? Or you have to add a evaluate method in the base class, and then you have to go to the binary AST node and you have to implement that evaluate method. You have to go to ternary AST node and you have to implement the associated evaluate method, so on and so forth. But that's a problem because you are kind of mixing up two different logics. Your AST node is a class hierarchy by itself. You want it to be clean, and you want to do different kinds of things on your AST, on your abstract syntax tree. But the particular approach that we have taken, so it kind of mixes up things. It kinds of every time you want to do some kind of traversal on your AST node, you have to touch your whole AST node, AST code base. And this is really bad. Like, for example, think of it that there are two, you and your friend, you are building a compiler and you are doing semantic analysis and he is doing code generation. So both of you are all the time working on the same code base, and it becomes a nightmare to work together. So this particular approach is not a clean approach for traversing the AST trees. The AST hierarchy is great, no problem, but traversing the ASTs, it's not a clean approach. So we use, in order to solve this problem, we use what is called as a visitor designer pattern. Visitor design pattern. So let's take the code. Great. So now if you see the AST node, let's see how the AST structure looks like here. So here you will have the AST node, this is the base class, and you have only one method called as an accept method. That's all. So your AST, and then there is a parameter to this accept method. It is an AST visitor. And then if you go look at the code for the binary AST node, everything else will be the same. And what you will see is this accept method has this code. Okay, we will see what it is. Essentially, what this accept method does is, so if a visitor, okay, let's say a semantic analyzer wants to visit an AST binary node, if a semantic analyzer wants to visit a binary AST node, it calls the accept function associated with the binary AST node. And the binary AST node, it accepts that call, and what it does is it responds back by calling the visit function, and it passes a handle to itself, no, to its own memory, so that the visitor can see what is present in that object and take some actions. Similarly, if you see ternary AST node, so there will be one function, line 99 to line 102. You can see that so the accept function is realized in this particular fashion. So how exactly all these things work, we will see in a moment. But the same is the case with the intlit node. So what is most important is this ast.h file, it is not going to change at all. It is going to remain the same throughout. You can have one person can write an evaluate traversal routine, another person can write a postfix traversal, another person can do a prefix thing, another person can do a code gen. All these visitors, each of these things, they are called as visitors, and these visitors they traverse the AST and do what they have to do. And you can see, for example, here, there is a postfix visitor. Let's see how this postfix visitor works. And before we see postfix visitor, we will see for every visitor, let's say if you want to write a, let's say write a postfix traversal, okay? Then what we do is, you can see there is a base class called as an AST visitor, and this base class has visit methods associated with different associated with the different AST node types. So there is a visit method for binary AST node. So this particular visit method is supposed to take care of handling binary AST nodes. And there is another visit method for ternary AST node, and there is another visit method for intlit AST node. So for every AST node type, or in this case for every AST node class type, you will have a visit method in this base class, AST visitor. And if you want to implement a new traversal or a AST traversal method process, then what you have to do is you have to derive this base class. You have to derive this base class AST visitor, and you have to implement all these methods. So for example, here I have the postfix visitor, and this postfix visitor, it derives the base class AST visitor. And remember, AST visitor has three visit methods. One visit method is associated with the binary AST node. Another visit method is associated with the ternary AST node. And another visit method is associated with the intlit AST node. So let's see what is happening. And then if you see the base code, so this is, there is some kind of code around, but what I would like you to focus is on line 36, for example, here. So here before what happened is you have already created a AST and you want to make a traversal on the AST. So you create a postfix traversal class object. On line 15, we are creating a postfix visitor traversal visitor object, postfix visitor object, PFV, and then using PFV, we want to visit or traverse the whole AST. And the way we are doing it is we start with the root node, and that's what we are doing here. So we are making on line 36, we are making a call to pfv.visit by passing the root node, by passing the root node of the AST to uh, the visit function. So let's say if the root node here is a binary node, it's a binary AST node. If the root node is a binary AST node, if the root node is a binary AST node, then what happens is this is the method that gets invoked. Okay, this is the method that gets invoked. And when this method gets invoked, so there is, so here we have, let me, yeah. So here, this is the root node. So this is the node. And then, so what we are doing is we are calling the left child's, so this visit function, what it is doing is it is making a request to the left child that I would like to visit you. Okay, I would like to visit you. That's what it is trying to do here. And then it is passing a handle of itself. That star this, it's a handle for itself. It's a handle for that PFE object. It is passing a handle of itself to this left chain. And similarly, it is calling, it is requesting the right child, hey, I would like to visit you. And when it is trying to visit a particular node, it presents itself, and that's what is the parameter. Presenting itself is a parameter. It provides a handle of itself to that to the node that it is going to visit. And after it visits the left and right child, all it does is it prints the node's binary operator. Whatever the, let's say if the binary operator associated with this is plus, it prints it. Similarly, when it goes to, if the node turns out to be a ternary node, then it has three children. It has three children. So it makes a request to the first node. Hey, I want to, could you please accept my, no, I want to visit you. And the way it makes that request is that visit request is to the accept method by invoking the accept method of the node. And when it makes a request, it presents itself. It provides a handle of itself to that node. So it tries to visit the first node, second node, and third node, and then it prints the ternary operator associated with that node. And this is how the postfix traversal works. So now what happens within that? So when you make a call to accept, when you make a call to what do I say? When you make a request to, when the visitor makes a request to the node through the accept function, what happens inside the accept function? Let's see. See, this is the accept. Yeah. So this is the accept function. Great. So here, let me. So here, this is what happens. So the way you have invoked, made a request to this particular node that I would like to visit is through this accept function, and you present a handle. And what this accept function is doing is it is invoking using this handle, using the handle provided by the visitor. It is telling the visitor, you know what, could you please traverse, okay, visit. It is making a kind of doing a callback. Okay, so by calling v dot visit star this, but this star this corresponds to the object with AST node. This is AST node. Okay. So now what happens is, let's say, so this is so this node is a ternary node with 3 children. So when this node says, when the node here, it says using this handle, it says v dot visit star this, where star this is nothing but the pointer to this object, okay, whatever that object handle. Then what happens is, depending upon the type of this parameter, if this turns out to be, if this child turns out, if this node turns out to be a ternary AST node, then what happens is the visit function, let me eraser. Yeah, the visit function associated with this method will be called, this particular method will be called. Okay, here you can see the visit function. This is a ternary node. So when that in the accept, when a callback is done using v dot visit, then what happens is, depending upon the parameter type to the visit, like for example here, if this is a ternary AST node, then the method that is there on line 13 will be invoked. All right. So this is how the whole AST traversal happens using the visitor design pattern. The very nice thing about this approach is, if you want to write a prefix traversal, you don't need to touch the ast.h file. All you have to do is, for example, Control A, Control C, Control N, Control V, and you just say prefix visitor. So as you work on, as your friend works on the postfix traversal, you can work on the prefix traversal. That's it. And the code base is very completely clean. The code for, the code for your AST code, it is there. Your AST structure is present. The code base is present in ast.h. And your postfix visitor is present in postfix visitor.h. And your prefix visitor code is present in prefix visitor.h. So the whole code base is completely separated from each other, and it is you can nicely manage your compiler infrastructure. In the absence of that, your whole ASTH file, it becomes a huge file, and with many methods in it, and it will be hard for people to work together, and it becomes a mess. So that is the purpose of the visitor design pattern. I hope you are all with me on the two approaches we took in realizing AST for ASTs and AST traversals using the object-oriented approach. Can I see how you are doing? If you understood what the discussion in today's class, can you acknowledge it in the chat box, or where you stand? Any questions? Yes. The AST part, the AST, the visitor designer pattern, you need to, you may want to see one more time to get a hang of it. When you see it for the first time, it looks a bit tricky, but you can, if you think about it a bit, you will understand it. Great. So to conclude the lecture, I will just take 5 more minutes. So those of you who have a class, you can drop off to, I want to show, because we just have seen the AST for AST structure only for expressions. But if you think of a whole program how it will look up, how it will be like, we will see. So Prajwal has the question on the number of lookups in visitor designer pattern won't be more. Yes, I think so, Prajwal, because I think when you use virtual functions, then yeah, so there could be some performance impact, but it will not be noticeable because it's all the memory accesses will increase, but overall the complexity of the traversal still remains the same. So you might still be doing all right. I'll just take 5 more minutes so that I can completely conclude the discussion on this. Sorry. How the AST, so now we are switching to Java, sorry, because I wrote this code long time back. So I thought I'll just use this. So how the AST looks for a whole program. So if you look at the AST for a whole program, if you see on line 4, there is an abstract base class called as AST node. All right. And then focus on line 8. On line 8, you are defining a AST node associated with for your whole program. And it derives and it is derived from the base class AST node. And what are all the fields present in this AST program class? There are 2 fields. Look at line 23. Line 23, it's the name of the program. Like for example, in decaf, you know, every program, it has a name. Okay, it starts with class program, left flower brackets, some statements, and then right flower brackets. So every program has a name in this particular programming language. So line 23, you store the name of the program, and line 24, pay attention that it is a array list of methods. Okay, it's an array list of methods. A program is a list of methods. So if you see on line 24, we have a variable which is of type array list, and each element in this array list, it is of type method declaration. So now let's go and see how a AST method declaration looks like. So if you go look at this AST method declaration, this code is not complete, but look at the lines 108 to 113. So every method, it will have a name. So that's what line 111 says. And then every method, it will have a body, which is nothing but a block statement. That is, it starts with left flower bracket and ends with right flower bracket. And then all the variables and parameters within that method, they will, and their associated types, you want to store in a symbol table. So there is a variable called as sim. It is a hash table essentially, which holds the variables and their associated data types. So this is how the AST node for a method looks like. Now let's go back here. So your program is a list of methods. So in the AST program, you have this variable which is of type array list, and every element in this array list, it points to a method declaration. And now let's look at, and you know, like your program and every method, it's a sequence of, it's a block statement or it's a sequence of statements. So if you see every statement in your program, it is derived from the base class AST node. And there are different kinds of statements. One is a block statement. If you see a block statement is derived from the class AST statement, and a block statement is nothing but a statement list. So if you see, there is a variable here called as statement list, and it is of type array list, and where each element in this array list, it is of type AST statement. And there are different kinds of statements, just not a block statement. There can be an assignment statement. If it is an assignment statement, you can see that there are 2 fields. One is one points to the location, that is the LHS, and another points to AXT expression, which is the second field. because that corresponds to the RHS. Similarly, a AST statement can be a method call statement. And you can see if it's a method call statement, you want to store information about the method and the parameters that you are going to pass, and the parameters that you are going to pass, they are stored in this expression list variable. Again, it's an array list where each element in this array list, it is of type AXT expression. Okay. So finally, I will just conclude with this. If you see line 76, this is the AST node associated with an AST statement. It has 3 fields in it. One points to an expression, and another points to the if part, and another points to the else part. Right? So like this, if you are, we can lift up the ideas that we have discussed in today's class and extend it to a whole programming language by defining an appropriate class hierarchy. And the question for you, the architectural question or the design question for you is, what is the principle that guides you in designing this class hierarchy? This is the core question that you should understand from today's class. What is the design principle you should be keeping in mind while coming up with this class hierarchy to represent the abstract syntax tree associated with a program? This is the core question I want all of you to think about. If you are able to come up understand this answer, if you are able to answer this question and get a clear idea about about the answer to this question, then it is fantastic. Then that means you completely understood the software architecture associated with the AST trees. This is number one. Number two is there are 2 traversal approaches we have seen. One is the naive approach. It has its problems, scalability problems. And the second approach is the visitor design pattern approach. So these are the 3 things that you need to understand. What is the principle behind designing the class hierarchy? Number 1. Number 2, what is the naive approach for traversing the ASTs? Number 3, how we can use the visitor design pattern to traverse the AST in a very clean manner. So these are the 3 points, 3 summary questions that you need to think about with respect to today's lecture. So with this, I conclude today's lecture, and if you have any questions, you can ask me now.